This is video 25 in the lecture on the design of reinforced concrete beams. This lecture deals with concrete cover and total depth of a beam. The total depth of a beam is based on three main criteria. The first is the use and comfort of the beam. For instance, it's like deflection. If the deflection is too big, it's not very interesting to have a floor with a very large deflection. The second criteria is stability. It's obvious that the beam must be able to carry the loads where it was designed for. And the third one is durability. It means that the beam must withstand the forces of nature during a certain period of time. The use and comfort, we can translate it into slenderness, which is defined as the span divided by the effective depth. And for stability, we can use the strength criteria. We are using the optimum. It means that with the optimum, the strain of concrete and strain of steel are maximum. We use the materials to their maximum capacity. You can also, in this criteria, you can also use the ductile, which is the depth where the behavior of the beam has a sufficient rotation capacity. Or we can use the minimum depth of the beam, which is that kind of depth of beam where the ductility where the yielding of the steel is just there. So it can be the optimum, it can be also different. It's on the designer's point of view what to choose, but in most cases we will use for stability the optimum. For durability or functionality, it's in fact the concrete cover that guarantees the durability. It's a concrete cover together with the quality of the concrete, of the grade of the concrete, of course, but the most important factor is the concrete cover. The total depth of the beam is then the depth required for strength plus the concrete cover and plus the stirrup diameter and the point of gravity of the reinforcement in tension. For slenderness, if you do not want to go to very large calculations, you can estimate the needed slenderness, L of D, with this formula. If the ratio of reinforcement is smaller than the ratio rho 0, which is square root of FCK divided by 1000. So it means for not very strong reinforced beams, then you can use this formula. Otherwise, for highly reinforced beams or beams with tension reinforcement, compression reinforcement, you should use this formula. So this gives only an estimate of the required span to depth ratio. In the previous formula, there was a factor K, and this factor depends on the structural system. If it's a simple supported beam, the K factor is 1. If it's a cantilever, the K factor is 0.4. And you will see now that the required slenderness, L over D, for highly stressed concrete, which means reinforcements of more than 1.5%, or for lightly stressed concrete with a reinforcement of 0.5%. And this is the required slenderness that you can use. So, for instance, if you have a simply supported beam and you have a slightly stressed beam, then you can use as a first step in the slenderness L over D equals 20. This is a way to quickly estimate the needed slenderness of a beam. The calculated sag of a beam subjected to quasi-permanent loads should always be the span divided by 250, and it should be the span divided by 500 for supporting structures. When there are small walls on a floor or on a beam, then the deflection should be less than the span divided by 500, or even 1000 sometimes. The calculated value of L of D is only valid for a steel stress of 310 megapascal in SLSQ. For other values of steel stress, the value L of D should be multiplied by a factor, which is 310 divided by sigma S, and sigma S you can calculate it just with a pro rata rule like this. Where does the 310 come from? Well, you can demonstrate it very easily. In ULS, the stress is FAK divided by 1.15. We have a mean load factor between 1.35 and 1.5. So say a mean load factor is 1.4. So it means 500, which is FAK, divided by 1.15 divided by 1.4 is 310 megapascal. That's all. That's all what this means. Now, let's take a heavily reinforced beam and a not so heavy reinforced beam, and we look at the simply supported beam. Then we see that we have L over 20 as the slenderness. We have L over 26 for the end span of a continuous beam, and we have L over 30 for an interior span of continuous beam. For a cantilever, L over 8. When it's heavily reinforced, we have then L of 14 for simply supported beam, L over 18 for the end span of a continuous beam, and L over 20 for the interior span of a continuous beam. And for a cantilever, L over 6. So there are a lot of numbers where you can choose from. So in practice, what we do is we take L0 divided by 15. This is the slenderness we start with. This is the slenderness to give us an idea what is the required depth of a beam. So L0 divided by 15. L0 is this length of beam where the bending moment is 0. So for a simply supported beam, L0 is equal to L, of course. So for an simply supported beam, L0 is equal to L. For a cantilever, it's L0 is 2 times L. For an interior span in a continuous beam, then the L0 is 0.7 L, and for an end span in a continuous beam, it's 0.85 times L. So we use this to have a quick estimate of the needed slenderness of a beam. Now, we know that the reduced bending moment is given by this formula, MSD divided by BD squared FCD, that we use for strength calculations, and the reinforcement is given by the bending moment divided by the lever arm, ZD times FAD. Zeta is Z over D, X over D is Xi, and mu D, the reduced bending moment. If we want to design the beam with yielding of steel, then mu D must be 0.371. The maximum should be smaller than that. With rotation capacity, the beam has a mu D of 0.296, and for an optimum use, for the optimum use of the materials, mu D must be 0.817. That we have seen in the previous lessons. The corresponding Xi, or the depth of the lever arm, is given by those numbers. Here you see the 0.45 because to have enough rotation capacity, X must be smaller than 0.45 times D. And Z over D, that's for easily calculating your reinforcement. So if you want to design a beam according to strength, for instance, you would like to have an optimum depth, then you use 0.187 in this formula. This is 0.187. The bending moment is there. You choose the concrete grade according to the environmental class, and you can calculate the D, the needed D. And if you got that, then you can easily calculate the reinforcement that you should need, or estimate the reinforcement that you should need. Then we have almost everything for the total depth, but now we need to know something about the concrete cover. How are we going to calculate the concrete cover? The concrete cover is the distance between the surface of the reinforcement and the nearest concrete surface. This is C nominal, this is this one. This for this bar here, if this is the nearest concrete surface, then C nominal is the concrete cover. For this bar, the concrete cover is C, is this one. This is a normal configuration for a beam. You have the tensile reinforcement, you have the stirrup around it, and then at the stirrup you have the C nominal, which we are going to calculate, and the C nominal is the minimum required concrete cover plus an amount C def, deviation from deviation, taking into account the human error. The nominal cover must always be specified in the drawings. This one. Not C min and not C def, but C nominal. We have now a section of a reinforced beam, compression reinforcement, tension reinforcement, the stirrup, technological reinforcement, total depth, and the width of the beam. And this is the effective depth. D is the effective depth, and D1 is the point of gravity of the tension reinforcement with respect to the most tensioned fiber. This is of course at one layer of reinforcement and using the same diameter. The total depth is then the effective depth that we have calculated. This can be, for instance, the optimum plus D1, point of gravity of the tension reinforcement, and D1 is the diameter. If it's the same diameter and the one layer of reinforcement, then the D1 is phi divided by 2 plus the diameter of the stirrup and plus the nominal cover, the concrete cover. How are we going to calculate now the concrete cover? We start with the concrete cover is the maximum of the C nominal that we are going to calculate and delta C, which is a surface coefficient. The surface coefficient is related to the formwork. If it's concrete casted against fixed formwork, then the surface coefficient is 0. When it's cast against prepared soil, then it's 40 millimeters. And when it's cast against soil or a PVC sheet, then it's 75 millimeters. So you see, if you just pour concrete like a foundation slab on a PVC sheet or on sand, then you have a concrete cover of at least 75 millimeters, and this will then be dominant. C nominal is delta C def plus C min. Delta C def, the error on C min, it's 10 millimeters in all cases. But if you have an increased quality control, it means that when you are really rejecting all elements that do not fulfill at a required concrete cover and you reject those elements, then you can use as delta C def 5 millimeter. But you must have an increased quality control. C min, that is the maximum of C min B, C min dur, and 10 millimeters, the maximum of the three. And C min B depends on the size of diameter of the tension reinforcement. And you have a maximum granulate size bigger than 32 millimeters, then it is the size of the diameter plus 5 millimeters. Otherwise, it's only the size of the diameter. And C min dur, this is the real required concrete cover for the durability of your beam. It's in a table, it's table 4.4N of Eurocode 2 part 11, and this is the table. It's just taken literally out of the code and pasted in this slide. So for reinforced concrete, and you have, for instance, a beam inside the house, and it's just the house, then you have a structural class S4, and then the C min dur is 15 millimeters. If you have a bridge, it's EE4, and it's S6 as a class, then you have at least C min dur of 55 millimeters. We have a similar table for pre-stressed concrete. The structural class, just to remind you, is S1 to S6, going from temporary structures to civil engineering structures like bridges. This is the design value of the years, the design years. So it's designed for 100 years. This is designed for 10 years. Recently, we use not S6 anymore, but this is in one group S5 for 100 years. So it's scrap. No, it's not valid anymore. And then they use it as S5 structural class. But we will still use the S6 because for me it's much more clear that we talk then about civil engineering structures and bridges. If you have monumental structures, then you calculate them in the S6 category. In most cases, 80 or 90% of all cases, it's buildings and bridges or quay walls or retaining walls. And so for buildings, it's a structural class S4, it's for 50 years. For bridges, it's structure class S6, and it's for 100 years. So that we must remember. Then this is taken out of the Eurocode. And you can see now for each environmental class and corresponding exposure classes, you can now increase or reduce the classes, the construction classes by 1 or 2. For instance, if you want to have a design working life of 100 years, and you have just a normal building, which is 50 years, and you want to design it for 100 years because a client asks, then you must increase your structural class by 2. For all environmental classes, you must add 2. So it means from S4 you go to S6, which is logic. If you use a concrete strength more than which is required, for instance, if you use for inside your house a concrete quality bigger or equal to C30, then you can reduce your class by 1. So you can design your house not in an S4 class, but an S3 class. It saves you on concrete cover, so it will save you in volume of concrete and so on. The same is valid for other environmental classes. If you have a member with slab geometry, it means that the position of the reinforcement is not affected by the construction process. It means most of the time it's for slabs and walls. Then you can also reduce the construction class by 1. And if you apply a special quality control of the concrete production, this for instance prefabrication, don't mix up with the delta C def, which was a quality control, an extra quality control on the concrete cover. This is a special quality control of the whole process, for instance for prefabrication. Then you can also reduce one, you can reduce by 1 construction class. So if you use a concrete strength which is more than the required one, and you have a prefab structure, then you can reduce by 2, which is a lot. It makes, most of the time this means that you can gain 10 millimeters on your concrete cover. When the environmental class is fixed, then you can have a corresponding concrete type. So for instance, for E1, the environmental class inside the house, inside the building, you should at least have a concrete type T.065. 0.65 is the cement water ratio. So now you can, for each environmental class, you can look up what is the required concrete type. And in this table, every concrete type gives you the maximum water cement ratio, the minimum cement content, and the minimum strength class. So now it's getting easy. You have your environmental class. From the environmental class, you look up in the table, what is my concrete type? And from the concrete type, you will see what is the minimum strength required. Let's just give an example of a very simple home in inland, somewhere in Belgium. It's reinforced concrete, it's cast in situ, it's a beam not exposed to rain because there is a concrete cladding coming in front of it, so it's not exposed to rain, it's just inside the building. There is a rebar diameter of 12 millimeter, no special quality control, with fixed formwork, and the maximum granulate size is 40 millimeters. So this is a very normal case. Now we know that the concrete cover is the maximum of those two elements. The surface number, because it's cast against fixed formwork, the surface number is 0. So we only take into account C nominal, and C nominal is the maximum of those three. So we look now at C min B, and we see that the maximum granulate was bigger than 32. So we use Vs plus 5. It means 12 plus 5 is 17. In most cases, you will not know the diameter that you are going to use. So you need some experience. You also do not know the maximum granulate size of the concrete. If you don't know, you put yourself on a safe side and you take the maximum. For Vs, you cannot take the maximum because this will be ridiculous. And if you have 32, that will be a little bit too much. So we start, in principle, we start for slabs at a diameter 12, and for beams, we start at a diameter of 20. Afterwards, you have to check this. And if this is not right, then you have to redo your calculation and correct it. But here in this exercise, it was set that the diameter was 12. So we continue with 12. Then we need to calculate the semi-dur. We have the structural class. It's a home, so it's S4. It means for inside the house, it's 15. So semi-dur is 15. It means that this is 17, 15, and 10. So the maximum is 17. And there is no special quality control on site, so this delta C def is 10 and the C min is 17, so the total required nominal cover is 27 millimeters. Of course, in reality, you will round it off to not to 25 because that's too little, but to 30 millimeters. But in fact, 27 is enough. Then how do you specify this concrete for this beam for your house? You start always with the environment, it's EI. The exposure classes, you find it in the table that we've seen before, it's X0, X1. In the table, you look up for E1, what is the type? It's T.0.65 The concrete quality also from the table is C1620, and the cover we calculated just now is 27, and the crack width that comes from also the table, but we know for the crack width it's always 0.3 millimeters, except for the environmental class EI. That's 0.4 millimeter. And this gives you the total information that you need to specify your concrete. Let's take a second example, staircases outside. It's just, you cannot see it, but it's outside. It's in contact with rain and frost. These are steps outside, and those steps are reinforced concrete, but they are prefabricated. The rebar diameter is 12. The special quality, there is a special quality control. There's fixed formwork, and it's a home in Brussels, and used concrete quality is C3037. We use the same method. The surface, because its coefficient is 0, because we use fixed formwork. Then Seaman B, we have a diameter of 12 millimeter as maximum diameter. We don't know that. There's nothing said about the maximum size of the granulate. In principle, because it's prefabricated, it should be smaller than 32, but it's not set, we don't know, so we take the maximum. So it's 17. For Semindur, we look it up in the table, this time for EE3, because this is a staircase subjected to rain and frost. We assume that there is no de-icing salt, because it's for a particular, it's not for public. It's not public that is allowed to walk on those steps. So maybe there will be some de-icing salt once or twice a year, but we will take this not into account. So it's EE3 and it's S4. EE3 means 30. But there's a quality control, so we can go -1 in the structural class, so it's not 30 but 25. Then we have Semin B was 17 plus Semindur 25 and 10, the maximum is 25. So the 25 comes here. Delta C def, it's prefabricated, so we can say this is not 10 but 5, so the total is 30 millimeters. And this is the total specification of the concrete EE3 with an exposure class XT4 XF1. This is outside at the rain, then this is in the frost. Type is T0.5. Concrete quality must be C3037. This is exactly the one which we are using. If we are using, for instance, here C40, then we can still go one structural class down again. The cover is 30 millimeters and the crack width is 0.3 millimeters. Now, all this is according to Eurocode 2 and according to the Belgium annex, and it's all written down in chapter 4. But it's written down in sentences, so it's sometimes quite difficult to see how it is really used in practice. I've now, for different environmental classes, I've calculated the needed concrete cover. And I've done that for buildings because that's most of the time the case. It means structural class S4, with no special quality control, no prefabrication, no slab geometry, because this is a course in beams, and on fixed formwork. So if you take this, which are 80% of all the cases, and you calculate for different bar diameters, the needed concrete cover, and you put it in a table, then something very nice comes out. Because you see a pattern, and the pattern is that the concrete cover is 15 millimeters plus the diameter of the reinforcement, the maximum reinforcement. And this is so for inside your house and for E0. For EE1, EE2, and EE3 and EE4, it's also 15 plus the bar diameter, but with a lower limit. So it should always be more than 35 for EE1 and EE2, and it should always be more than 40 for EE3, and it should be more than 55 for EE4. So if you use this as a rule of the thumb, you can estimate very quickly your needed concrete cover. Especially when it's buildings for inside, you know directly your concrete cover should be 15 plus the maximum diameter you use as reinforcement. We can do the same for elements at the coast and for elements in an aggressive environment. And you will see we obtain also the same result. It's always 15 plus phi, but for ES 1, 2, 3, and 4, you see that the concrete cover must be always bigger than 45, 50, and 55. Now, we can summarize all this because it's a lot to grasp, and therefore, if you use this table, it's easy to start and to calculate needed height of a reinforcement, the net depth of a needed depth of a cross section of a beam. You start with the environmental classes. Remember, it was the memory aid: frost, rain, and salt, or de-icing salt. Then you know this is 0, 0, 0, and these are the little crosses. So you know EE3 is with frost and rain. EE2, it's only with frost. So if you put that, E1 is inside buildings and E0 is no risk. And then you put next to it the nominal cover, needed nominal cover, and you see it's 15 plus the diameter. And for EE1 is at least 35 for EE1 and EE2. EE3 it's 40 and EE4 it's 55. So now you can, in a very quick way, start calculating the total depth of a beam. We have the same table for ES1, ES2, ES3, and ES4, frost and in contact with air. It's just the summary of what we have seen, and you have the similar table. You can now establish the needed total depth of a beam, concrete cover included. See you at next lecture.